Hi again. This is our second work. It is on community detection on static graphs using LPA or label propagation algorithm. It is a fast algorithm, but it identifies communities of medium quality. Here we are proposing a memory efficient GPU-based approach. The size of real-world graphs is large, and therefore, on shared memory systems, we are hitting the memory usage limits, particularly when we are using many threads. Memory efficiency is actually underexplored in common detection. There exist streaming algorithms which address this issue, but their single pass nature results in obtaining communities of lower quality. State-of-the-art implementations achieve good performance. They have high memory usage due to the per vertex hash tables. Our approach is as follows. For each vertex, we choose the best possible label in LPA given the labels of its neighbors. So each neighbor has an associated label C and an associated linking weight. But we replace the per vertex hash table with a sketch, a Misragiri sketch. In the sketch, we aggregate the community label and the associated sketch value. Once all the neighbors have been processed, we choose the label with the highest sketch value. This is done for vertices with low degree. For high degree vertices, we maintain multiple misagree sketches, aggregate them separately, and then combine them together into a single consolidated misagree sketch, and then obtain or select the community with the highest sketch value. Now let me go through the reasoning behind this step by step. First, our mission is to replace the per vertex hash table with a sketch, which is small in size and fixed, which makes it suitable for a GPU. We are going to use a misagree sketch, which has k slots and or a Boyer-Moore majority vote algorithm, which is essentially k equals to 1. The misagree algorithm essentially identifies k majority uh, labels among the neighbors if there are majority. Here, the definition of majority is the total weight of a majority label should be greater than the total weight of all labels by k plus 1. In the end, after scanning all the neighbors, we get k candidate labels with associated sketch value. We can then do a second scan to compute the exact linking weights. So the Mr. Grease algorithm is as follows. We want to accumulate a label C and associated weight into the sketch. So in the sketch, if a slot has C, we simply add W to the slot. Otherwise, we try to find an empty slot and add it to it. If there is no empty slot, we decrement W from all the weight other slots. We assign for processing one thread per slot and one cooperative group per sketch. Cooperative group is required in the case where the number of slots is less than 32. Mr. Gray's algorithm has two synchronization points. One, to check if a slot has C, and the other one is to find an empty slot. For this communication or synchronization, we can use a shared variable, let's say has, and here we must synchronize all threads before accessing this shared variable. If the sketch, however, is shared between multiple threads, we need to use atomic operations such as atomic add to accumulate the weight, and atomic compare and swap to fill an empty slot. Instead of using a shared variable, we can use vault level voting instructions such as ballot to find C in a slot or to find an empty slot. and all to check if any thread succeeded to populate the empty slot. We also need to determine a suitable value for k. A lower value of k will result in a faster execution time or lower execution time, but lower community quality as well. A high k will result in a slower algorithm but high quality communities. We can then partition the vertices in the graph into two sets. Low degree vertices are processed using a group per vertex approach, cooperative group per vertex, and high degree vertices using a thread block per vertex approach. In the block per vertex approach, the miscellaneous sketch is shared between multiple threads or multiple cooperative groups, and therefore each slot is updated by multiple threads. In the group per vertex approach, the sketch is not shared, and therefore no atomic operations or retry loops are needed. Actually, what we can do, we can replace shared sketches with partial sketches for the block per vertex approach, as Mr. agrees sketches are mergeable. That is, we can maintain separate sketches for each subset of neighbors, and then we can merge them together to obtain the final Mr. sketch. And this is identical using a shared Mr. sketch. But this requires additional work and space. The way the merging will happen is all thread groups except the first thread group merge into the first sketch. And this approach is actually faster than using a shared sketch. We can also avoid a second scan to find the exact community link weights and just use the sketch value to determine the most popular label for a vertex. And this is actually faster without sacrificing on community quality. We optimize the parameters of this implementation using manual gradient descent. That is, we adjust k and the other different parameters, such as when to consider the degree of a vertex to be high or low. Using manual gradient descent means we adjust each parameter slightly and observe the impact. If it improves performance, we accept the change, and then we change the other parameter. We see if it improves the performance repeatedly until we obtain no further improvement in performance. We use the same dataset as earlier, and we compare with NetworkKit LP, which is a parallel multi-core implementation. But here we are unable to accurately measure the memory usage of the algorithm because of the way it allocates memory. We also compare with GV-LPA, a parallel multi-core implementation, and 𝜈LPA, a parallel GPU-based implementation of LPA. We do not compare with 𝜈LPA because it is obtaining low-quality communities for at least this data set, and Cougar flow where we observe that it is 37 times slower than 𝜈LPA, although it does obtain communities of 10% higher quality or modularity. This is the memory usage comparison. Here, lower is better, and the y-axis is logarithmic scale. If you observe 𝜈MG 8, where k equals to 8, LPA, and Boyer-Moore LPA, both have lower memory usage compared to the other implementations. It is 2.2 times lower memory usage than NetworkKit, and 98 times lower than GV-LPA, and 44 times lower than 𝜈LPA. On 𝜈LPA, on the SQ 2005 graph, it turns out of memory, and therefore the line is or the bar is not drawn for it. Now this is the performance comparison in terms of runtime. Here, lower is better. Y-axis is again logarithmic. Runtime of 𝜈MG 8 LPA is lower than other implementations. It is roughly 51 times faster than NetworkKit LPA and 2.4 times than GVLPA, but 1.1 times slower than 𝜈LPA. It's roughly similar performance. Next, coming to modularity, the modularity of communities obtained by 𝜈MG 8 LPA is good, particularly on web graphs and uh, communities, social network graphs, but is lower on neural networks and protein schema graphs. Uh, this is also the case for new LPA, and it is likely due to the significant parallelism available, which prevents exploration of all possible cases or all possible community assignments. Roughly, it is 8.4 times percent lower modularity than networked LPA on average, and 2.9% lower modularity than new LPA. Therefore, we recommend new MG-LPA to be used for web graphs and social networks. So, in conclusion, uh, our approach could be adapted to dynamic community detection as well as other graph problems such as link prediction and graph partitioning. Thanks a lot. Have fun.